Now it's time to talk about how we see atoms today, the birth of modern atomic theory. Where are the electrons? The constant question. Dalton, of course, knew nothing about the structure of the atom. He thought it was a hard sphere. Thomson discovered electrons and helped us to see that maybe they acted like raisins on the surface of a pudding. Rutherford gave us the nuclear planetary model using his gold foil experiment. Bohr gave us, again, a nuclear atom, but he said that the electrons orbited only in distinct energy levels, specific shells. The Bohr atom was a nuclear atom. It left the electrons free outside the nucleus to be given away or shared. The Bohr atom didn't collapse, and he said it doesn't collapse because it doesn't collapse. The electrons can't get any closer than the first energy level. Bohr explained the emission spectra of atoms as the change in energy levels as electrons at high energy levels relaxed and moved to a lower one. By doing so, they would emit only specific energies, specific frequencies and wavelengths of light. But Bohr didn't explain why or how the electrons could orbit only at specific distances or energy levels, and he had no explanation of how it is that molecules have a specific shape, because as electrons were running around and around the nucleus, they weren't inhabiting a specific region of space. But we know in reality now that molecules do have a specific shape. In fact, that's how biochemistry works. And if our molecules didn't have a specific shape, we couldn't exist as human beings. Furthermore, the Bohr atom's math only worked for single electron systems, not for anything with multiple electrons. And so the Bohr atom, although in advance, was not the final answer. Well, that leads us to ask, what is an electron? Now, we assume that it's like a little BB, a tiny hard sphere with a negative charge. But Einstein's study of the photoelectric effect, which appeared in 1905, stunned science. He showed that light, which is electromagnetic energy, can act not just like a wave, but like a particle, a packet of energy. He called the packet a photon. In other words, the light that we see, or ultraviolet or X-ray or whatever it is, comes in what some people call wavicles, things that have properties of both particles and waves. Louis de Broglie then came along and asked, well, why can't a particle act like a wave if a wave of light can act like a particle? And he asked, is the electron also acting like a wave? Well, experiments showed that electrons can act like waves of light, very high energy, short wavelength light. That's why we can use electrons to light up very small cellular structures in an electron microscope, such as the one you see pictured here. This is a fly's foot as imaged by an electron microscope. Very high energy light. What is the electron's wavelength? Well, it depends upon its velocity. The wavelength of any particle is going to be equal to Planck's constant divided by the momentum, which is the mass times the velocity. So just for fun, let's use Planck's constant, which is about 10 to the negative 33rd joules seconds, to calculate the velocity of a more common object, say your teacher or your coach. Now, the coach's wavelength is going to depend upon the coach's velocity. Again, the wavelength is equal to Planck's constant divided by the momentum. Now, in order of magnitude, coaches are about 10 to the second kilograms and can move about 10 to the 1 meters per second, about 10 meters per second at top velocity. So, The wavelength is 10 to the negative 33rd divided by 10 squared times 10 to the 1, or 10 to the negative 36 meters. Now that sounds very short. You're right, it's very, very short because the smallest atom is about 10 to the negative 11th meters in size. This is an extremely short wavelength. So it's too small to observe even at top speed. What's the electron's wavelength? Again, it depends upon the velocity. So we'll assume that in the vicinity of the nucleus, the velocity of these electrons is 10% of the speed of light, would be about 10 to the 7th meters per second. The electron's mass is very small, 10 to the negative 30th kilograms. So when we take this and do the multiplication in the denominator and then divide that into the numerator, we get 10 to the negative 10th meters. This is a much longer wavelength than anything that you can see, like a coach, and it could be used to light up a very small structure like a cell organelle. For instance, here, this is the photomicrograph of a mitochondria, and it looks very much between the picture and the diagram, very much like what you have studied in biology. So why do we take this trip into finding the electron's wave nature? Well, we wanted to find out how the electron can behave when close to the nucleus. We've been thinking of it like a planet going around the sun. It'll help us understand why the electron can only inhabit certain energy levels, and how can it get from a high energy level to a lower energy level without going anywhere in between. Now, we've diagrammed here a standing wave on a string, and we set the frequency so that there is a null spot or node here and here. The wave actually is moving, has a positive value here and here. The waves are generated at the end of the string down here, and they vibrate at just the right frequency, so that the parts of the string vibrate well here and down here, but not at all at the nodes. The wave has a zero value here and here. We can demonstrate this on a guitar or banjo string by plucking it in the middle. I'll do that on my guitar string here. We pluck it in the middle. And now I'm going to hold the middle down and pluck it halfway between the middle and the end. I am not fretting this. Even when I pull my finger away, it continues to vibrate, but not in the center. A tone one octave higher is generated. Both sides are vibrating, but they're vibrating twice as fast. That's called the first overtone for those of you in music. This man is demonstrating how to set up higher and higher frequency standing waves on a string. And you can see, as he shakes the string faster and faster, you get more and more nodes on the string. 3 nodes here, 2 here, 1 here, and it only is vibrating not at all at the ends here. It's obvious that only standing waves with a whole number of lobes, areas that are vibrating, 2 here, 1, 2, 3 here, 1, 2, 3, 4 here, only a whole number of lobes and a whole number of nodes, 1, 2, 3 here, can happen at all. And if you try this yourself, you'll see that the more lobes and nodes you have on the string, the more energy is needed to keep it going. It's fun to do this, for instance, with a slinky. So, if the electron in the vicinity of the nucleus is acting like a wave, obviously it can only have certain energies, because it can only, quote, vibrate at certain frequencies. And when it changes from a higher to a lower energy, there really is nothing in between. So here at the ground state, and here at the first excited state, there's nothing in between because the electron is acting like a wave. There's nothing in between because the electron is acting like a three-dimensional standing wave, and there are no energies between the allowed standing wave energies. Well, some people would still like to look at the electron as a particle, so quantum mechanics gives you a model to think about, but it's not a planet revolving about the sun. Think about what the standing wave below looks like. It looks all fuzzy, doesn't it? You don't really know where the string is at any given point of time. Only the nodes are clearly seen. So let's talk in terms of probability. There's zero probability of the wave at the nodes and maximum probability of the wave in the middle of the lobes. So let's think of a particle that we've all had to play probability games with in our lives, especially here in South Texas. It's a mosquito flying around you. I call this the bug in the box. Does a mosquito fly in a predictable path? You don't have to discuss that. You know it doesn't. They fly in unpredictable paths that make sense only to them. They're trying to avoid getting killed or eaten or both. And so you can see the mosquito running all over the place. Now here's 2 seconds of a mosquito's life that we've captured in a single picture. Can you tell the path she took? Answer, of course not. You can tell the probability of the mosquito being somewhere. Where is the highest probability of finding the mosquito? Well, obviously, it's there. Why do you think the mosquito spends so much time there? Looking for food. Looking for your arm. So let's think of the electron like the mosquito. Electrons around the nucleus can also be considered as particles without knowing their paths. A mathematical equation is used to describe the probability of finding them in any given place. And on our next video, we will show you that equation and what we can do with it.